Hello everyone, this is part 12 through 14 of the practice exam. Alright, let's look at part 12, the binomial theorem, and we'll have one question like this on the real exam. Okay, so we have to use the binomial theorem to expand each polynomial, and let me just remind you what the binomial theorem says. So it says a plus b to the n is equal to the following sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. This one I have memorized because it's quite useful. Okay, so that is your formula, the binomial theorem. All right, so in this case, a is 2x, that's a, and then y squared is b, and then 6 is n. All right, so those are the things that you need to use in this formula. So we're going to get that this is going to be the sum from k equals 0 to 6. So I'm putting 6 in for n. And then it's going to be 6 choose k. And then we're going to have a. Be careful to put a in parentheses. Okay, so 2x is in parentheses, so it all gets this exponent. Oops, the n is going to be 6. Sorry. So this will be 6 minus k. And then b, put that in parentheses as well. Okay, and then this is going to be to the k. Okay, so now that you have all that in, and the only variables left are x, y, and k, go ahead and expand the summation, and then at the end we'll simplify it. So first I'm going to plug in k equals 0, so this will be 6 choose 0, 2x to the 6 minus 0, y squared to the 0, and then I'm plugging in 1 for k, so 6 choose 1, 2x to the 6 minus 1, y squared to the 1. All right, I'll come back down to the next line, and then plus 6 choose 2, 2x to the 6 minus 2, y squared to the 2, 6 choose 3, 2x to the 6 minus 3, y squared to the 3. You just keep going like this until you get to 6. It's kind of boring. You can fast forward if you want. Okay, and now you have to simplify it a little bit more. So I'm going to look up what all of those combinations are, and then I'm also going to be using some rules of exponents and things to also simplify the 2x part being raised to an exponent. So like you have to raise the 2 to the exponent, you also have to raise the x to the exponent, and then when you have y squared to another exponent, you're going to multiply those two exponents together. Okay? Alright, so 6 choose 0 is 1, and then we have 2x to the 6, so this is going to be 2 to the 6 and then x to the 6, and then we have y squared to the 0, so that's just going to be 1. Then 6 choose 1 is 6, and then we have 2 to the 5th and x to the 5th, and then we have y squared to the 1, so that's y squared. And then 6 choose 2 is 15. I'm actually just looking at Pascal's triangle to do that. And then this is 2 to the 4th, x to the 4th, and then y to the 4th as well. So 2 times 2, 4. And then we have 6 choose 3, which is 20, and then 2 to the 3, x to the 3, and then y is going to be to the 6th. And then we have 6 choose 4, which is going to be 15 again, and then 2 to the 2, x to the 2, and then y is going to be to the 8th. And then we have 6 choose 5, which is 6 again, and then we have 2 to the 1, x to the 1, so I guess I don't need to write that. And then we have y to the 10th. And then finally 6 choose 6 is 1. And then we have 2x to the 0, so I don't need to write that because that's 1. And then y to the 12th. Okay, and then I'm just going to multiply some of these together and do the powers on the 2's. Okay, so this is going to be 64x to the 6th plus 192 x to the 5th y squared plus 240 x to the 4th y to the 4th plus 160 x cubed y to the 6th plus 60 x squared y to the 8th plus 12x y to the 10th, and then finally just y to the 12th. And that is the final answer there with complete simplifications. All right. Okay, so we're going to expand another one with the binomial theorem. So let me just remind you what the binomial theorem says. A plus b to the n is the sum from k equals 0 to n of n choose k times a to the n minus k, b to the k. All right, so we're going to apply that to this by making a into 3x, and then negative y, make sure you get the negative there, is going to be b, and then 5 is going to be n. So if we use this formula, then we get the sum from k equals 0 to 5 of 5 choose k times 3x. Make sure you put that 3x in parentheses so it all gets the exponent. So this will be, sorry, that's not any character. 5 minus k exponent there, and then make sure you put the negative in with the y, and that'll be to the k. All right, so then we're going to expand this by just plugging in all the values for k from 0 to 5. So this will be 5 choose 0, 3x to the 5 minus 0, negative y to the 0, and then 5 choose 1, 3x to the 5 minus 1, negative y to the 1, and then 5 choose 2, 3x to the 2, negative y. Sorry, I did that wrong, didn't I? This should be 5 minus 2 there. And then this one is to the 2. Okay, and then 5 choose 3, 3x to the 5 minus 3, and then negative y to the 3. And then 5 choose 4, 3x to the 5 minus 4, and then negative y to the 4. And then finally, 5 choose 5, 3x to the 5 minus 5, and then negative y to the 5. Okay, and so from here I just need to simplify all of this. So I'm going to simplify the exponents. I'm going to apply each exponent separately to the 3 and to the x. And then also for negative y, I'm going to do negative y raised to each power, so I'll do the negative and the y part separately. And then I need to simplify all of these choose expressions using either Wolfram Alpha or calculator or Pascal's triangle to figure out what they all are. Okay, so I'm going to come through and do that. So 5 choose 0 is 1, and then I'm going to have 3 to the 5, and then x to the 5, and then negative y to the 0 is just 1, so I don't need to write that. 5 choose 1 is 5, and then I'm going to have 3 to the 4, and then x to the 4, and then I'm going to have negative y, and that's just the 1, so I don't need to write that. And then 5 choose 2 is 10, and then I'm going to have 3 to the 3, and then I'm going to have x to the 3, and then negative y squared is just positive y squared. Okay, then 5 choose 3 is 10 again, and then I have 3 squared, and then x squared, and then negative y cubed is the same as writing it like this, so it just has the negative once there. Okay, and then 5 choose 4 is 5 again, and then I have 3, and then I have x, just to the 1 power each, and then negative y to the 4th is the same as y to the 4th. And then finally 5 choose 5 is 1, and then 3x to the 0 is also 1, and then I have negative y to the 5th, which I can write with just one negative like that. Okay, and then I just need to make another pass through there again and multiply all the coefficients together, put the negatives in front. So when I do that, I get 243 x to the 5th minus 405 x to the 4th y, and then 270 x cubed y squared, and then minus 90 x squared y cubed, and then plus 15 x y to the 4th, and then finally minus y to the 5th. And that is the whole final answer there. Okay, let's look at number 3. So again, I'm going to use the binomial theorem, so let me, oops, that's the wrong side. Let me write what that is. So a plus b raised to the n is equal to the sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. So in this case, my a is x, and then my b is 2y squared, and then my n is 4. Okay, so let's go ahead and use the formula. So this will be the sum from k equals 0 to 4 of 4 choose k times x to the n minus k, and then make sure you put the 2y squared part in parentheses for b, and then that's going to be to the k. Okay, so let's go ahead and do this sum. I'm going to plug in all the values for k from 0 to 4. So the first will be 4 choose 0, x to the, oops, I think this should have been a 4 right here, right? That should have been a 4. So x to the 4 minus 0, and then 2y squared to the 0, plus 4 choose 1, x to the 4 minus 1, 2y squared to the 1, plus 4 choose 2, x to the 4 minus 2, 2y squared to the 2, and then the last two terms, 4 choose 3, oops, and then x to the 4 minus 3, and then 2y squared to the 3, and the last term, 4 choose 4, x to the 4 minus 4, 2y squared to the 4. All right, and now I just need to simplify all of these exponents and coefficients, distribute the exponents, figure out what these choose expressions stand for. So 4 choose 0 is 1, and then we have x to the 4th, and then 2y squared to the 0 is also 1, so I'm not going to write that part. And then 4 choose 1 is 4, and then we have x cubed, and then we have 2y squared just to the 1 power. Okay, then 4 choose 2, that is 6, and then we have x squared, and then we have 2y squared, so that's the square, sorry, 2y squared squared. So the square is going to come down and be on the 2 there, and then y is going to be to the 4th power, because we multiply the exponents together. All right, then 4 choose 3 is 4, and then we have x to the 1, and then we have 2y squared cubed, so the cube power is going to go on the 2, and it's also going to go on y squared to make y to the 6th. And then 4 choose 4 is 1, and then x to the 0 is also 1, and then we have 2y squared to the 4th, so the 2 gets the 4th power, and then the y squared also gets the 4th power and becomes 8. All right, and then we just need to simplify a little bit everything again. So this will be x to the 4th, and then this will be 8x cubed y squared, and then 24x squared y to the 4th, and then 32x y to the 6th, and then 16y to the 8th. And that's it. Okay, let's look at part 13, which is on graphs, and there will be one question similar to this on the real exam. Okay, number 1, so we're going to answer the questions for this graph. So the first question is the graph simple? So a simple graph is one that has no parallel edges and no loops, so this is not simple. So the answer is no, it has parallel edges. For example, E2 and E4, as well as E6 and E7. You don't have to put that much detail in your answers, but that's just so you understand. Part B, is the graph connected? So yes, it is connected, and the reason there is because we can reach any vertex from any other vertex by walking along edges. Maybe I should say, oh, I left out the word reach. I should have used the word walk anyway, since that's the technical term that we learned. So we can walk from any vertex to any other vertex. Okay, what is the total degree of the graph? So I'm just going to go around all the vertices and add up their degree. So this one has 2 little edges coming out, so that's 2. This one has 4 edges coming out, so that's 4. This one also has 4, and then this one has 2, and this one has 4. Okay, So that is going to be a total of 16. So I'll just write down my calculations here. All right, does the graph have an Eulerian circuit? If so, list it. So an Eulerian circuit is one where you visit every vertex and you visit every edge, and you cannot repeat edges, but you can repeat vertices. So let me see if I can find one by going around this graph. Let's see. So if I start, oh, actually, there's a way to test for this, isn't there? So if every vertex has an even degree, then there should be one. So let me write that down. So every vertex has an even degree. So yes. All right, and now let's try to find one. So maybe I can just go around the outside first. And then if I go back down here and then I come back up, then I think I'm starting and stopping at the same point, which is something that you have to do. So let me write that down. So I'm going to start at V2 and go along E1 to V1, and then along E8 to V4, and then along E5 to V3, and then along E4 back to V2. And then I'm going to go down E2 to V5, and then I'm going to go down along E7 to V4, and then I'm going to come back up E6 to V5, and then I'm going to come back up E3 to V2. Okay, so I started and stopped at the same point, and I went through every edge exactly once, so that is an Eulerian circuit. All right, does this graph have a Hamiltonian circuit? If so, list it. Okay, so a Hamiltonian circuit, first of all, it has to be a simple circuit, so we cannot repeat any edges, and we cannot repeat any vertices, but we do have to visit every vertex once. So you want to look at the vertices, first of all, that have degree 2. There's only one way to enter and exit from those vertices. So if I want to get to V1, I have to enter and exit through those 2 edges that I just highlighted. And it's the same deal with V3. So I have to enter and exit V3 through those 2 edges. But then once I've done those 4 edges, I can't add anything to this because that would require me to visit some vertex more than once, because I would have already visited all 4 of these vertices, and then there's no way for me to get to V5. Okay, so this one does not have a Hamiltonian circuit, and I'm not asking you to explain why it does or doesn't, just to answer the question. So, but I'll just put an explanation in parentheses here for your sake. So we have to enter and exit E1 through E1 and E8, and we have to enter and exit V3 through E4 and E5, but once we have those 4 edges, we can't add anything else. Okay, let's look at part 2. Is the graph simple? So this graph has a loop and it has 2 parallel edges, so it is not simple. So I'll just write that down. So the parallel edges are E2 and E3, and it also has a loop, which is E6. Is the graph connected? Yes, it is connected. I can walk from any vertex to any other vertex along a series of edges. So when you're taking the test, you don't have to write these explanations, but I'm just doing them so you'll understand. What is the total degree of the graph? So let me go around and check all the vertices. So this one has 1, this has 1, 2, 3, 4, this has 1, 2, 3, 4, 5, this one has 2, this has 1, 2, 3, 4, 5. This has 1, 2, 3. Okay, so the total degree is 1 plus 4 plus 5 plus 2 plus 3 plus 5. So that should be 20. All right, and then does the graph have an Eulerian circuit? So it's not going to have one because of what we discussed previously, that there's a test, which is whether all the vertices have odd degree. So no, because not all the vertices have even degree. So they all have to have even degree in order to have an Eulerian circuit. Does the graph have a Hamiltonian circuit? If so, list it. So this is a circuit by which you could visit every vertex exactly once. So you cannot repeat edges, and you also cannot repeat vertices. So the answer here is going to be no, and I'm focusing on this V0 part to see that the answer is no. So we can't visit V0 without repeating an edge, so we would have to repeat E1, and that would not then be a Hamiltonian circuit. All right, let's look at the third one here. Is the graph simple? So in this case, it is simple because there are no repeated there are no parallel edges and there are no loops. Now, is the graph connected? So in this case, you might be a little bit fooled if you just glance at it, but it is actually not connected. So it's two completely separate triangles, and there are no vertices where those triangles are crossing at, so you cannot get from one triangle to the other triangle along an edge. So it's two disconnected triangles. Okay, so for example, you cannot get from vertex U to vertex Z along any sequence of edges. What is the total degree of the graph? So I believe it's 6 vertices and they all have degree 2. So this is going to be 12. Does the graph have an Eulerian circuit? So the answer is going to be no, because it's disconnected. So you can't visit every edge along a single circuit because it's disconnected. And then the same with the Hamiltonian, it's going to be no, for the exact same reason. We can't visit all the vertices in one visit, or in one circuit. Okay, now let's look at part 14, which is also graphs, but it's a little bit different style of questions. And there'll be one question like this on the real exam. Okay, so for each of the questions in this part, we have to either draw a graph that satisfies the description or explain why no such graph exists. So I'm just going to do 2 questions per slide here. Okay, so number 1 is binary tree, height 4, 8 terminal vertices. So remember that a binary tree is a rooted tree where each parent has at most 2 children. So I'm going to start by drawing a very skinny binary tree of height 4. So here's my root, and then this is height 1, height 2, height 3, and then height 4. So this one only has 1 terminal vertex, which you can see there at the bottom. So let me try to add some more without increasing the height. So here's a second terminal vertex, and then that parent can't have any more children. So let me put 1 more terminal vertex here, and then I need some more, so let me just kind of keep going with this. There's a couple more, so now I've only got 4. Let me try to do some more. Oops, I gotta try to keep these on the same level, right? Okay, so maybe go in there, and then have 1 down here, and then there. Okay, that's only 6, so let me just try to do a couple more. All right, now I think I'm to 8. Right, so this is a height 4 binary tree with 8 terminal vertices, and then there's lots of different ways that I could have drawn this, but this is just one way to do it. All right, let's look at the second one. So the second one is a full binary tree with 7 vertices. So a full binary tree is a binary tree where every parent has exactly 2 children. So there's only really a few ways to draw it, depending on the height is the only way they can be different. So here is a full there's a full binary tree of height 1, and then a full binary tree of height 2 would look like this, and I think that already takes me to 7 vertices right there. So that is that one. Okay, so let's look at number 3. We need a full binary tree with 12 vertices. So a full binary tree, what this means is this is a tree, a rooted tree, I should say. Rooted tree where every internal vertex has 2 children. So let's see if we can draw this, and I think that we actually can't, and I want to explain why it is not possible. So you start with one vertex, the root, right? And then whenever you go to add children to that, you have to add them 2 at a time. So you add children 2 at a time. So we could keep going on like this, adding pairs of children. But think about what you're doing. You started with 1, and now you're adding them in pairs. So you start with 1 and you add pairs, and then so you must end up with an odd number of vertices. So this is actually not going to be possible because 12 is not odd. I apologize for if you guys can hear my cat banging on things in the background. So this is not possible because 12 is even. Okay, so let's look at number 4, a tree with 9 vertices and 9 edges. So this is also not going to be possible because a tree with n vertices has n minus 1 edges. So if it had 9 vertices, it would need to have 8 edges. So this is not possible. Let's look at number 5. So a tree with 5 vertices and a total degree of 8. All right, let's see if this is possible. So I'm going to draw 5 vertices. So I'll just put them in kind of like a circle. And let me try drawing a tree and see if I can do this. So I could just do like a really boring tree that's just like this. So that would be 1, 1, 2, 2, 2. Oh, I did it. Okay, that was fast. All right, so this does have total degree 8. And it is a tree because there's no circuits. Okay, part 6. Graph, 6 vertices, 5 edges, not a tree. All right, so let me just try putting 6 vertices down, and let me try to put 5 edges down in such a way that it's not a tree. So I definitely don't want to just go around in a chain like I did on the last one, because that would be a tree. So I'm going to have to put some kind of a loop in here. So let me try doing like a triangle to be a circuit. All right, so now it's not a tree, and I just need to put 2 more edges. So I'll just put them there and there. Okay, so it didn't say that it had to be connected, so this is not going to be connected. Okay, let's look at the last one here. A graph connected with 6 vertices, 5 edges, and contains a circuit. So this is not going to be possible, and I will tell you why. So I'm going to refer to theorem 10.5.4, which says a connected graph with n vertices and n minus 1 edges is a tree. So this graph would have to be a tree because we're plugging in 6 for n, and so n is 6 and n minus 1 is 5. So this graph would have to be a tree, so it can't contain a circuit because trees have no circuits. Okay, and that's it. Alright, that's it for the practice exam solutions. If there was anything that you didn't understand, just send me an email and I'll be happy to clarify any points for you. Good luck!